The screen opens in absolute darkness. Then slowly, almost imperceptibly, tiny fluctuations begin to shimmer across the void like ripples on a cosmic pond. These aren't random. They're the universe's first whispers. Quantum fluctuations stretched to astronomical proportions by cosmic inflation 13.8 billion years ago. As we watch, these delicate variations in density begin to grow. Dark matter responding to gravity's patient pull, forming invisible scaffolds that will one day cradle entire galaxies. The camera pulls back slowly, revealing a growing web of filaments and nodes, each representing regions where matter is beginning its billion-year journey from chaos to order. Gas follows the dark matter's lead, falling into these cosmic wells, heating up from the violence of its own collapse, then slowly cooling as atoms shed their energy into the darkness. What you're witnessing unfold in these moments actually took 3 billion years, longer than life has existed on Earth, longer than our solar system has orbited the galaxy, longer than the gap between the first dinosaurs and today. This is the universe's ultimate slow-motion movie, where every frame represents millions of human generations, where patience isn't just a virtue, but the fundamental requirement for complexity to emerge from simplicity. Now imagine trying to tell this story at its natural pace. If we started our documentary when the first galactic seeds began forming and played it in real time, every human civilization in history would rise and fall millions of times over before we reached the first chapter. This is why galaxy formation remains one of the most challenging stories to tell, not because it's complicated, though it certainly is, but because it unfolds on timescales that dwarf human comprehension. We live our lives in seconds, minutes, hours, measuring important events in years or decades, yet the cosmic processes that created our galactic home operate on scales where a million years is barely a tick of the clock. To understand how galaxies are born, we must recalibrate our sense of time entirely, embracing a perspective where geological epochs become mere moments and the rise and fall of species become background noise to the slow dance of dark matter and gas. This is the story of the longest birth in the universe, longer than the formation of planets, longer than the evolution of stars, longer than anything else we know. It's a story that began when the universe was young and hot and smooth, and it's still happening today in distant corners of space where new galaxies are taking their first breaths. Every atom in your body was forged in nuclear furnaces that only exist because this slow birth succeeded billions of years ago, creating the cosmic cities we call galaxies, where stars could form, live, die, and scatter their enriched ashes into space. You are made of galactic stardust, shaped by processes so gradual that they make continental drift look hurried, yet so fundamental that without them, the universe would be nothing but a cold, dark, empty expanse devoid of stars, planets, or the possibility of wonder itself. In the beginning, there was darkness, but it wasn't empty. The universe's first 380,000 years were dominated by a thick fog of plasma so dense that light couldn't travel more than a few inches before being absorbed and re-emitted. When this fog finally cleared during an epoch we call recombination, it revealed something extraordinary: the cosmic microwave background, a nearly perfect map of tiny temperature variations across the entire sky. These variations, detected by satellites like Planck, show us density fluctuations of only 1 part in 100,000. Ripples so subtle they would be invisible to the naked eye, yet they contained within them the seeds of every galaxy that would ever exist. Dark matter, making up roughly 85% of all matter in the universe, responded to these density variations first. Unlike ordinary matter, dark matter doesn't interact electromagnetically, meaning it doesn't absorb or emit light, doesn't feel pressure from radiation, and doesn't experience the complex physics that governs ordinary atoms. This simplicity became its superpower. While ordinary matter remained tightly coupled to the radiation field, unable to collapse because photons kept pushing it around, dark matter could simply follow gravity's call, slowly aggregating in the regions where density was even slightly higher than average. Computer simulations reveal this process with breathtaking clarity. Starting from nearly uniform conditions, dark matter begins forming what physicists call halos, roughly spherical concentrations of invisible matter bound together by gravity. These first dark halos were tiny by cosmic standards, perhaps containing only as much mass as a small star, but they grew through a process of hierarchical assembly. Smaller halos merged to form larger ones, which merged to form larger ones still, creating an intricate web of filaments and nodes, each representing regions where matter is beginning its billion-year journey from chaos to order. Gas follows the dark matter's lead, falling into these cosmic wells, heating up from the violence of its own collapse, then slowly cooling as atoms shed their energy into the darkness. The hierarchical nature of dark matter assembly means that large galaxies like our Milky Way are actually archaeological sites, containing within their structure the remnants of hundreds or thousands of smaller halos that merged over cosmic time. The smooth, seemingly uniform dark matter halo surrounding our galaxy is actually a complex ecosystem of substructure, streams, clumps, and debris from ancient merger events. Each of these features tells a story about gravitational encounters that happened billions of years ago, creating the invisible architecture that would ultimately determine where stars could form and how they would be distributed across space.
Once dark matter had begun carving out the universe's fundamental architecture, ordinary matter, primarily hydrogen and helium gas left over from Big Bang nucleosynthesis, could finally begin its own journey toward galaxy formation. But this journey was far more complicated than dark matter's relatively straightforward gravitational dance. Gas has pressure, temperature, and complex interactions with radiation that make its behavior much more dramatic and unpredictable. When gas falls into a dark matter potential well, it doesn't simply settle gently into place. The gravitational energy of its fall gets converted into heat through a process called thermalization. Gas falling from the edge of a forming galaxy halo can reach temperatures of millions of degrees, hot enough to emit X-rays and create what astronomers call a virial shock, a spherical boundary where infalling gas suddenly heats up and slows down. This creates a fundamental problem for galaxy formation. Hot gas has tremendous pressure that wants to push it back out of the gravitational well it just fell into. The solution lies in the gas's ability to cool itself through radiation. Hot gas is full of energy, and atoms and ions in the gas can shed this energy by emitting photons across the electromagnetic spectrum. In the early universe, when only hydrogen and helium were available, cooling was limited to a few specific processes. Hydrogen could emit Lyman alpha photons, helium had its own emission lines, and in extremely dense regions, molecular hydrogen could form and provide additional cooling through rotational and vibrational transitions. This cooling wasn't instantaneous. It could take hundreds of millions of years for gas to settle into the bottom of dark matter potential wells. The cooling process creates a beautiful feedback loop that regulates the rate of galaxy formation. Gas that cools too quickly might collapse so rapidly that it overshoots equilibrium and creates unstable conditions. Gas that cools too slowly might never settle into a stable rotating disk. The Goldilocks zone for galaxy formation requires cooling times that are comparable to the dynamical time, the time it takes for material to orbit within the dark matter halo. This delicate balance helps explain why galaxies didn't form instantly after dark matter halos appeared, but instead required hundreds of millions of years to assemble their first stable structures. Conservation of angular momentum plays a crucial role in determining the final shape of these gas distributions. Even tiny amounts of rotation in the initial gas cloud get amplified as the gas contracts, just like a figure skater spinning faster as they pull in their arms. This rotation prevents all the gas from falling directly to the center of the dark matter halo, instead causing it to settle into a rotating disk. The thickness and extent of this disk depend on the amount of angular momentum the gas possessed and how efficiently it could cool and settle. Primordial star formation. The first stars to ignite in the universe faced challenges that no star today has to overcome. Born from pure hydrogen and helium gas in an era before any heavy elements existed, these population 3 stars had to trigger nuclear fusion under conditions dramatically different from the stellar nurseries we observe in modern galaxies. Without elements like carbon, oxygen, or silicon to facilitate cooling, star-forming gas clouds could only contract by radiating energy through molecular hydrogen, a much less efficient coolant that required extremely specific conditions to form and survive. These primordial gas clouds collapsed to much higher temperatures before they could fragment into individual stars, typically reaching several thousand degrees compared to the tens of degrees typical of modern star formation regions. The high temperatures meant that only very massive gas clouds could overcome their own thermal pressure to collapse under gravity, leading to the formation of stars that were likely tens or even hundreds of times more massive than our Sun. These stellar giants lived fast and died young, burning through their nuclear fuel in just millions of years, compared to the billions of years that smaller stars can sustain fusion. The death of population 3 stars was spectacular and transformative.
Their massive size meant they ended their lives as pair-instability supernovae, explosions so violent that they completely obliterated the star, leaving no remnant behind. These explosions released tremendous amounts of energy and, more importantly, scattered newly forged heavy elements throughout the surrounding gas. For the first time in cosmic history, carbon, oxygen, neon, magnesium, silicon, and iron became available in the interstellar medium, fundamentally changing the physics of subsequent star formation. The transition from population 3 to population 2 star formation marked a crucial turning point in galactic evolution. Even tiny amounts of heavy elements, astronomers call them metals regardless of their actual chemical properties, dramatically increased the cooling efficiency of gas clouds. Carbon and oxygen atoms provided new pathways for radiating energy, allowing gas to cool to much lower temperatures and fragment into smaller pieces. This meant that subsequent generations of stars could span a much wider range of masses, including the smaller, longer-lived stars that could sustain nuclear fusion for billions of years. The spatial distribution of these early supernovae also helped determine the large-scale structure of forming galaxies. The explosions created hot bubbles of gas that could expand to enormous sizes, carving out cavities in the dense gas and driving turbulence that would influence star formation for millions of years. Some explosions were energetic enough to drive gas completely out of small dark matter halos, effectively shutting down star formation until the gas could cool and return. This feedback process helps explain why small galaxies tend to have much lower stellar densities than large ones. Their shallow gravitational wells couldn't retain gas heated by supernova explosions. Early galactic assembly. The first billion years of cosmic history witnessed a period of intense galactic construction that astronomers call the Epoch of Reionization. During this era, the universe transformed from a cold, neutral hydrogen fog into the hot, ionized plasma we observe today between galaxies. This transformation was driven by the collective ultraviolet radiation of billions of newly formed small, actively star-forming galaxies scattered throughout the cosmic web. Early galaxies bore little resemblance to the majestic spirals and ellipticals we see in the nearby universe. Observations from the James Webb Space Telescope reveal that high redshift galaxies were typically much more compact, irregular, and actively forming stars at rates that would consume their available gas reserves in just a few 100 million years. These systems were undergoing rapid assembly through frequent mergers with other small galaxies, creating chaotic environments where gas was constantly being stirred up, heated, and cooled in complex cycles. The merger process itself was a crucial driver of galactic evolution during this epoch. When two gas-rich galaxies collide, their gravitational interaction can funnel large amounts of gas toward the central regions, triggering intense bursts of star formation called starbursts. These events could increase a galaxy's star formation rate by factors of 10 or more compared to its normal baseline, rapidly converting gas into stars and fundamentally altering the galaxy's structure and appearance. Gas accretion from the intergalactic medium provided another crucial source of material for growing galaxies. Computer simulations show that early galaxies were embedded in networks of cold gas filaments that could channel material from large distances directly into galactic centers. This cold mode accretion was most efficient in smaller halos, where infalling gas could avoid being heated to the virial temperature and instead maintain temperatures low enough to continue cooling and contracting. The efficiency of early star formation was regulated by a complex interplay of cooling, feedback, and gas supply. Galaxies that formed stars too rapidly would quickly exhaust their gas reserves and fade into obscurity, while systems that formed stars too slowly might never achieve the stellar masses necessary to retain gas against supernova-driven winds. The most successful early galaxies were those that achieved a balance between these competing effects, sustaining moderate levels of star formation over extended periods, while gradually assembling larger and more stable structures. Chemical evolution played an increasingly important role as early galaxies aged. Each generation of massive stars lived, died, and enriched the surrounding medium with heavy elements, gradually changing the conditions for subsequent star formation. The metallicity of star-forming gas increased over time, leading to more efficient cooling, lower characteristic stellar masses, and the formation of the first truly long-lived stellar populations that could survive to the present day.
The transformation from chaotic, irregularly shaped early galaxies to the organized disk systems that dominate the present-day universe required solving one of the most fundamental problems in galactic dynamics: how to convert randomly moving gas into a coherently rotating stellar disk. This process, which astronomers call disk settling, operated over timescales of billions of years and required precise coordination between gravitational forces, gas dynamics, and stellar feedback processes. Angular momentum conservation provided the fundamental physics underlying disk formation. Even tiny amounts of rotation in the initial gas distribution became amplified as material contracted under gravity, just as a figure skater spins faster when pulling in their arms. However, the mere presence of angular momentum wasn't sufficient to guarantee disk formation. The gas also needed to dissipate energy efficiently enough to settle into a thin, rotationally supported configuration, rather than remaining in a thick, pressure-supported spheroid. The settling process was mediated by complex interactions between different components of the galaxy. Dark matter, which doesn't experience dissipative processes, remained in a roughly spherical halo configuration throughout the galaxy's evolution. Gas, however, could lose energy through radiative cooling while conserving angular momentum, allowing it to spiral inward and settle into progressively thinner configurations. This gas eventually formed stars, which inherited the orbital properties of their parent gas clouds and thus naturally populated the emerging stellar disk. Feedback from star formation played a crucial role in regulating the disk settling process. Stellar winds, supernova explosions, and radiation pressure from massive stars could heat and stir the gas, temporarily halting the disk settling process and maintaining some vertical thickness in the disk. Too much feedback could completely disrupt disk formation, while too little could lead to excessively rapid settling and the formation of unstable, gravitationally bound stellar systems. The formation of spiral arms represented one of the most beautiful consequences of disk dynamics. These aren't permanent material structures, but rather propagating density waves that sweep through the stellar disk like traffic jams moving through a highway. The spiral pattern is maintained by gravitational instabilities in the disk that create regions of enhanced stellar density, which in turn trigger new star formation and create the bright blue regions we observe in spiral arms. The pitch angle and number of arms depend on the disk's mass distribution, rotation curve, and the efficiency of stellar feedback processes. Central supermassive black holes began influencing galactic evolution more strongly as disks became more organized and gas could more efficiently funnel toward galactic centers. The growth of these supermassive black holes through accretion released tremendous amounts of energy that could heat surrounding gas and regulate both star formation and the continued growth of the black hole itself. This created a self-regulating system where the black hole's mass became closely correlated with the properties of its host galaxy's bulge and overall stellar mass. At the heart of nearly every massive galaxy lies a supermassive black hole containing millions or billions of solar masses compressed into a region smaller than our solar system. The formation and growth of these cosmic monsters represents one of the most dramatic aspects of galactic evolution, with profound implications for star formation, gas dynamics, and the ultimate fate of their host galaxies. Understanding how these black holes formed so early in cosmic history and grew to such enormous masses remains one of the most active areas of research in modern astrophysics. The seeds of supermassive black holes likely formed through several different pathways in the early universe. Direct collapse of primordial gas clouds could have created intermediate mass black holes with masses of thousands or tens of thousands of solar masses, providing a head start on the growth process. Alternatively, population 3 stars might have collapsed to form stellar mass black holes that subsequently grew through accretion and mergers. Recent theoretical work has also explored the possibility that primordial density fluctuations could have directly formed black holes without requiring stellar intermediates. Regardless of their initial formation mechanism, these seed black holes faced a fundamental challenge: growing from stellar masses to supermassive scales within the first billion years of cosmic history. The maximum rate at which a black hole can accrete matter is limited by the Eddington limit, the point at which radiation pressure from infalling material becomes strong enough to halt further accretion. Growing from 100 solar masses to 1 billion solar masses in 1 billion years requires sustained accretion at close to this theoretical maximum, a feat that demands nearly perfect conditions for funneling gas toward the black hole. The relationship between black holes and their host galaxies became increasingly intimate as both grew together over cosmic time.
Computer simulations revealed that the most efficient pathway for black hole growth involves major galaxy mergers, which can drive large amounts of gas toward galactic centers and trigger episodes of rapid accretion. During these active phases, the region around the black hole becomes an active galactic nucleus, or AGN, outshining the entire stellar population of the host galaxy and launching powerful jets of plasma that can extend millions of light years into intergalactic space. Feedback from growing black holes fundamentally altered the evolution of their host galaxies. The energy released during accretion episodes could heat gas throughout the galaxy, temporarily shutting down star formation and driving galactic winds that expelled material into the intergalactic medium. This AGN feedback helps explain several observed correlations in galaxy properties, including the tight relationship between black hole mass and bulge velocity dispersion, and the observed decline in cosmic star formation rates after the universe's peak epoch around 10 billion years ago. The co-evolution of black holes and galaxies created a self-regulating system that determined the final properties of both components. Galaxies that grew too rapidly would feed their central black holes efficiently, triggering strong feedback that would halt further growth. Systems that grew too slowly might never achieve the gas densities necessary for efficient black hole accretion. The most massive galaxies achieved a balance between these extremes, sustaining moderate levels of both star formation and black hole growth over extended periods, while gradually building up the stellar populations and black hole masses we observe today. Fine-tuning the machine. After billions of years of chaotic assembly, galaxies gradually evolved into the finely tuned systems we observe in the local universe. This maturation process involved the establishment of stable equilibria between competing physical processes: star formation and stellar feedback, gas accretion and galactic winds, black hole growth and AGN feedback. Understanding how these equilibria emerged and how they regulate ongoing galactic evolution provides crucial insights into why galaxies exhibit such regular properties despite their complex formation histories. The regulation of star formation represents perhaps the most important aspect of galactic fine-tuning.
Modern spiral galaxies convert their available gas reserves into stars at a rate that would exhaust their fuel supply in several billion years, yet they have maintained steady star formation for most of cosmic history. This apparent contradiction is resolved by ongoing gas accretion from the intergalactic medium, which replenishes the fuel supply, and stellar feedback processes, which regulate the efficiency of star formation within available gas reservoirs. Stellar feedback operates through multiple channels that each become important under different conditions. Massive stars produce strong stellar winds and intense ultraviolet radiation that can heat and ionize surrounding gas, reducing its density and making it more difficult to form subsequent generations of stars. Supernova explosions inject tremendous amounts of energy into the interstellar medium, creating hot bubbles that can drive galactic-scale winds and remove gas from star-forming regions. Type A supernovae, which occur in older stellar populations, provide a delayed feedback mechanism that can influence star formation billions of years after the initial stellar birth episode. Chemical evolution continues to play an important role in regulating star formation and determining stellar properties. Each generation of stars that lives and dies enriches the interstellar medium with heavy elements, gradually changing the cooling properties of star-forming gas and the characteristic masses of newly formed stars. Galaxies with higher metallicities tend to form lower mass stars on average, leading to stellar populations that live longer and contribute different amounts of feedback energy to their surroundings. The interstellar medium itself becomes increasingly complex as galaxies mature, developing a multi-phase structure with regions of vastly different temperature, density, and ionization state coexisting within the same galactic disk. Cold molecular clouds provide the raw material for star formation, while hot ionized plasma fills the volume between clouds and can transport energy and metals across large distances. The boundaries between these phases are dynamic and constantly evolving in response to stellar feedback, turbulence, and gravitational instabilities. Environmental effects become increasingly important as the universe ages and galaxies become more tightly clustered into groups and clusters. Gravitational interactions between neighboring galaxies can trigger enhanced star formation through tidal torques that drive gas toward galactic centers. Ram pressure stripping occurs when galaxies move through hot intercluster gas, which can remove their own gas reservoirs and effectively shut down star formation. These environmental processes help explain the observed morphology-density relation, where elliptical galaxies are more common in dense environments and spiral galaxies dominate lower-density regions.
Cosmic ecology. Galaxy evolution in the mature universe is increasingly dominated by environmental effects and gravitational interactions between neighboring systems. Like biological ecosystems, galactic environments create complex webs of interaction where the properties of individual galaxies depend not only on their own internal processes, but also on their relationships with neighboring systems and the larger cosmic web in which they are embedded. Galaxy clusters represent the most extreme environments in the universe, containing hundreds or thousands of galaxies bound together in gravitational wells dominated by dark matter and filled with hot X-ray emitting plasma at temperatures of tens of millions of degrees. Galaxies falling into these clusters experience a variety of environmental effects that can fundamentally alter their evolution. Ram pressure stripping occurs when the galaxy's motion through the hot intracluster medium creates a wind that can strip away the galaxy's own gas reservoir, effectively shutting down star formation and transforming spiral galaxies into gas-poor ellipticals over timescales of a few billion years. Tidal interactions between galaxies become increasingly common as the universe ages and systems fall into progressively denser environments. Even relatively distant encounters can trigger dramatic changes in galactic structure, driving gas towards central regions and triggering starbursts, disrupting stellar orbits and creating tidal streams, or, in extreme cases, completely disrupting smaller galaxies through tidal shredding.
The remnants of these interactions can be observed today as stellar streams, shell structures, and other fossil evidence of ancient merger events. The most dramatic form of galaxy interaction is a major merger between two systems of comparable mass. These events completely reshape both participants, typically destroying pre-existing disk structures and forming new elliptical galaxies through violent relaxation processes. Major mergers are also highly efficient at driving gas toward galactic centers, triggering both intense starbursts and rapid black hole growth that can result in luminous quasar activity visible across cosmic distances. Galaxy groups, containing tens of galaxies in intermediate density environments, provide laboratories for studying environmental effects under less extreme conditions than galaxy clusters. In these systems, tidal interactions and minor mergers can gradually transform galaxy properties over extended periods, leading to the formation of fossil groups dominated by a single massive elliptical surrounded by a hot gas halo containing the disrupted remnants of former group members. The cosmic web itself influences galaxy properties through the anisotropic distribution of matter and the preferred directions along which gas can flow into forming systems. Galaxies located at the intersection of multiple filaments have access to larger gas reservoirs and tend to be more massive and actively star-forming, while systems in voids experience reduced accretion rates and may cease star formation earlier in their evolution. Looking toward the future, the ongoing expansion of the universe will gradually reduce the density of matter and the rate of galaxy interactions, leading to what astronomers call the stelliferous era, a period lasting trillions of years during which existing stars will slowly burn out while new star formation becomes increasingly rare. Eventually, even the longest-lived red dwarf stars will exhaust their fuel supplies, and galaxies will fade into invisible collections of stellar remnants, planets, and black holes, drifting through an increasingly empty universe. Yet this distant future should not diminish our appreciation for the remarkable complexity and beauty of galactic evolution during the universe's current epoch, when billions of galaxies continue the slow work of transforming primordial gas into the stars, planets, and perhaps life itself that make our cosmic environment so rich and varied.
The camera pulls back slowly from a vibrant spiral galaxy, its arms glowing with the light of billions of stars, each one a nuclear furnace converting hydrogen into heavier elements that will someday become the building blocks of planets, atmospheres, and perhaps life itself. As we retreat further, the galaxy shrinks to a point of light among countless others, each representing the culmination of a construction project that has been underway for over 13 billion years. This is where our journey through cosmic time has brought us, to the realization that we are not merely observers of galactic evolution, but participants in it, products of it, witnesses to a story that began when the universe was a fraction of its current age, and will continue long after our own sun has exhausted its fuel and faded to a cold white dwarf. The profound patience required for galaxy formation stands in stark contrast to the urgency that often characterizes human existence. We measure our lives in decades, our civilizations in centuries or millennia, our species' existence in hundreds of thousands of years. Yet the galaxies that surround us have been slowly assembling for billions of years, operating on timescales that render human history invisible. If the entire age of the universe were compressed into a single year, human civilization would occupy only the last few seconds before midnight on December 31st. The galaxies we see today began forming when this cosmic calendar was still showing January and February, growing slowly and steadily through cosmic spring, summer, and autumn, while countless worlds formed and died without ever being observed by conscious beings. This temporal disconnect reveals something profound about our place in the cosmic order. We are not accidents or afterthoughts in galactic evolution. We are its natural consequence. The slow pace of galaxy formation wasn't an obstacle to overcome, but a fundamental requirement for complexity to emerge.
Stars needed billions of years to forge the heavy elements essential for rocky planets and organic chemistry. Stellar populations needed time to evolve from the massive, short-lived giants of the early universe to the smaller, longer-lived stars capable of maintaining stable planetary systems for the eons required for life to evolve from simple chemistry to consciousness. The chaotic, merger-driven assembly of early galaxies had to give way to the more stable, organized structures we see today before environments suitable for complex chemistry could persist long enough to generate the intricate molecular machines we call living organisms. Every atom in your body tells a story of galactic evolution spanning cosmic time. The hydrogen in your DNA was forged in the Big Bang itself, emerging from the universe's first few minutes when temperatures and densities were sufficient for nuclear fusion, but not yet cool enough for atoms to form. The carbon that forms the backbone of every organic molecule in your cells was created in the nuclear furnaces of massive stars that lived and died billions of years ago, their explosive deaths scattering these precious heavy elements into the interstellar medium where they could be incorporated into subsequent generations of stars and planets. The iron in your blood was forged in the final moments of a supernova explosion, when the core collapse of a dying star created temperatures and pressures so extreme that silicon nuclei were crushed together to form iron group elements before being blasted into space at speeds of thousands of kilometers per second. The calcium in your bones, the oxygen you breathe, the phosphorus in your ATP, all were manufactured inside stars and dispersed by stellar winds and supernova explosions across the galactic disk. You are quite literally made of recycled stellar material, your atoms having potentially resided in dozens of different stars over the course of galactic history before finally coming together in the molecular arrangements that constitute your physical being. This isn't merely poetic metaphor, but scientific fact. Spectroscopic analysis reveals that the heavy elements in your body could only have been produced in stellar nucleosynthesis, and the relative abundances of these elements in your tissues match the predictions of stellar evolution theory with remarkable precision. The James Webb Space Telescope has revolutionized our ability to observe galaxy formation in action, peering back through time to witness galaxies as they appeared when the universe was only a few 100 million years old. These observations reveal baby galaxies in the process of assembling their first stellar populations, irregular and chaotic systems that bear little resemblance to the majestic spirals and ellipticals that populate the nearby universe. By studying these distant systems, we can literally watch galactic evolution unfold, seeing the same processes we've traced through theoretical models and computer simulations actually occurring in the early cosmos. Current observations are revealing surprises that challenge our understanding of how quickly galaxies could assemble their stellar populations. Some of the most distant galaxies observed by JWST appear more massive and more highly evolved than theoretical models predicted, suggesting that the efficiency of early star formation may have been higher than previously thought, or that supermassive black holes may have influenced galactic evolution even earlier in cosmic history than we realized. These discoveries remind us that despite decades of progress in understanding galaxy formation, we are still learning fundamental facts about how these cosmic cities assembled from the primordial hydrogen and helium that emerged from the Big Bang. The future of galactic evolution stretches ahead for trillions of years, far longer than the universe has already existed. Over the next few billion years, the ongoing expansion of space will gradually reduce the density of matter and slow the rate at which galaxies can accrete new material from their surroundings. Star formation will gradually decline as available gas reservoirs are either consumed or heated by stellar feedback to temperatures too high for gravitational collapse. Our own Milky Way will eventually merge with the Andromeda Galaxy, creating a new elliptical system that astronomers have dubbed Milkomeda, an event that will occur roughly 5 billion years from now, coincidentally around the same time our Sun evolves into a red giant star. Far in the future, after all the gas has been converted to stars or expelled from galaxies entirely, stellar evolution will enter its final phases. The most massive stars will have long since exploded as supernovae, leaving behind neutron stars and black holes. Intermediate mass stars like our Sun will evolve through planetary nebula phases before settling into white dwarf configurations. The smallest red dwarf stars will continue burning their hydrogen fuel for trillions of years, outlasting every other category of stellar object and providing the last sources of light in an increasingly dark and empty universe. Eventually, even these longest-lived stars will exhaust their fuel supplies, and the universe will enter what cosmologists call the degenerate era, populated only by stellar remnants, planets, and black holes orbiting through space in increasingly large and sparse gravitational systems. On even longer timescales, quantum mechanical processes may cause protons to decay, eventually dissolving all matter except black holes, which themselves will eventually evaporate through Hawking radiation over timescales so vast that current physics can barely comprehend them. Yet this distant future should not diminish our wonder at the remarkable epoch in which we find ourselves. We live during what may be the most interesting period in cosmic history, when galaxies are actively forming stars, when supermassive black holes are growing through dramatic accretion episodes, and gravitational interactions between galaxies are driving spectacular mergers and triggering intense starbursts that can be observed across billions of light years. We exist at a cosmic moment when the universe is old enough for complex chemistry and biology to have emerged, but young enough that the stellar furnaces powering galactic evolution still burn brightly across the sky. Every night when you look up at the Milky Way stretching across the dark sky, you are seeing the accumulated light of hundreds of billions of stars whose births span most of cosmic history, arranged in spiral patterns that have been sustained by density waves propagating through the galactic disk for billions of years. You are witnessing the ongoing work of cosmic evolution, the slow transformation of primordial gas into the stars, planets, and ultimately the conscious observers capable of contemplating their own origins in the nuclear fires that forged the very atoms of their existence. The story of galaxy formation is ultimately the story of how the universe learned to create complexity from simplicity, structure from chaos, and consciousness from chemistry. It is a story of patience and persistence, of physical processes operating across timescales that dwarf human comprehension, yet somehow conspiring to create the conditions necessary for understanding itself. We are the universe's way of knowing itself, temporary arrangements of stellar debris that have achieved the remarkable ability to reconstruct their own cosmic history and contemplate their place in the vast, slow dance of galactic evolution that continues around us every moment of every day. In this sense, the long birth of galaxies is not merely a scientific story about the formation of cosmic structures, but a deeply personal narrative about how we came to exist in a universe capable of creating beings that can appreciate the beauty and complexity of their own origins among the stars.